Hello everyone. Through this lecture, we are going to discuss a very short, a mini chapter on constitutive relations. Now, instead of just presenting you these relations, let me see if I can motivate the need for these relations. Now, what we have done till now is in the first chapter, we discussed the kinematics, uh, and in the second one, we discussed stress. And through these discussions, we presented a number of equations. So let's take stock of what we have till now and what we possibly need. Okay, so first of all, we especially while discussing the balance of linear momentum, I stressed very much that we are very much taking into account the balance of mass. Okay, so the balance of mass uh, or mass conservation, we have this continuity equation. And again, I want to emphasize that although perhaps we first studied this continuity equation in the context of fluid mechanics, but this is something which is very much uh, applicable for solid mechanics also. In fact, for any continuum mechanics studies. Now, in this equation, how many unknowns do we have? We have the rho, the density, which in general we'll consider as unknown. In addition to that, we have the three unknown components of the velocity vector. Now, especially in the kinematics chapter, the first chapter on kinematics, we did not really talk about velocities, unlike fluid mechanics. Instead, we talked about the displacement vector. But you all know from your earlier studies that the velocity vector is defined in this fashion. Okay, and it was also mentioned earlier. So the velocity vector can be defined as the material time derivative of the displacement vector. So when we are talking about the velocity vector, we can alternatively think of that we are actually talking about the displacement vectors, because if we know the displacement vectors, we certainly know the velocity vectors. Okay, so in this equation we have the number of unknowns as rho, one of them, and three velocity vectors, alternatively the three displacement vectors, so four in total. Okay, so let's say like this: rho is one unknown, and the velocity or the velocity vector or the displacement vector, that gives us three unknowns. Next, from the balance of linear momentum, we ultimately arrived at this particular equation. We actually arrived at the Cauchy's equation of motion, but considering static equilibrium, we arrived at this equation. Now here you see how many unknowns are here. So I am implicitly embedding within this equation the information that sigma is equal to sigma transpose. And if you remember from the previous chapter on stress, I had mentioned that from the balance of angular momentum, we arrive at this equation provided we don't have any body couples present. So you can consider that from this balance of linear momentum, where we actually use the balance of mass and we're also using this balance of angular momentum, so all of that information is encapsulated in this equation. And how many really how many unknowns are present here? So in this sigma stress tensor, we have 6 independent components, and these we'll consider as unknowns. Okay, so in this sigma there are 6. So in total, how many we have? 1 plus 3, 4 plus 6, 10 unknowns till now. And these are the equations that we have. So we have how many equations here? So this is a single equation, and this here is basically 3 equations. Okay, so we have mentioned that the expanded version of this would be the 3 stress equilibrium equations written in the form del sigma 1 1 del x1 plus del sigma 1 2 del x2 plus del sigma 1 3 del x3 plus rho b1 as the first component, and similarly for the second component and the third component. So in total we have 3 equations here and 1 equation here. So overall we have 4 equations. So this is just one equation, and this one is 3 equations. Okay, so overall we have 4 equations here, and here we have 10 unknowns. So we have 4 equations, but we have 10 unknowns. So we have a 6 equation discrepancy. So the easy fix is to introduce 6 equations, and we are going to do that through this constitutive relations by presenting this constitutive relations. But you will see that there is a subtlety involved there. Now, where do we get this constitutive relations? So in a very simple fashion, very roughly speaking, for these constitutive relations, we rely on experiments. Okay, and you have been exposed to these kinds of relations in your first year mechanics study as well as in your second year fluid mechanics or thermofluid science courses. I'm sure all of you remember the Hooke's law and the generalized Hooke's law. What we are going to present is again a version of that, but it is important to remember that when we are talking in general about constitutive relations, okay, so these constitutive relations, it is not just that the constitutive relations is just a fancy way of saying Hooke's law. Okay, so constitutive relations is much more general. So you can have various different combinations of relations between the stresses and the strains, between the stresses and the velocities, and together this entire possibility, the entire this entire list of possibilities of relations, those are commonly captured by this term constitutive relations, and Hooke's law is just one single very simple example of that, but very widely used all throughout the engineering domain. So for the purpose of our current course of mechanics of solids, we are going to discuss this generalized Hooke's law again, but what we'll say is that we'll try to make it a little bit more refined. So what we'll say is that we are interested in linear, elastic, isotropic materials. Much in the same way that when you were considering Newtonian fluids, you definitely considered linear and isotropic behavior. We did not mention the word elastic there because we didn't need it there, but now we need it. So that's what we'll say, that the kind of materials that we will be dealing with exclusively in our course of mechanics of solids will be linear, elastic, isotropic materials. Okay, so this is very important. So linear, elastic, isotropic materials. Now when we do that, what is the relation we have? So earlier in your first year mechanics, when we talked about generalized Hooke's law, you first of all express the various components of the strains in terms of the stresses. Now we'll take a different approach. We'll try to express the stresses directly in terms of the strains, and that we'll do in the next page. So and because we are somewhat familiar with the index notation, let's try to express it like that. So for linear, elastic, isotropic materials, what we have is this particular relation. So what is this basically? What is going on here? So you notice first of all that this lambda and this g, these are what are referred to as the Lamy parameters. Basically these are two material constants. Okay, so these two are material constants. Furthermore, this term epsilon kk, you note that this is basically using the repeated index. So we'll have this, the expanded version of this as epsilon 11 plus epsilon 22 plus epsilon 33. You also note that whenever we have uh, uh, this I not equal to j. So suppose we have sigma 1 2 or sigma 2 3 or sigma 3 1, then this term is not going to appear because we already know that when I is not equal to j, this Kronecker delta, it gives us a 0, in which case what we'll have is something like sigma 1 2 is equal to twice g epsilon 1 2. Okay, and sigma 2 3 is equal to twice g epsilon 2 3, sigma 3 1 is equal to twice g epsilon 3 1. It is only for the normal stress components, the sigma 1 1, the sigma 2 2 and the sigma 3 3, that will have the presence of this term, and in that particular case this term is only going to contribute to 1. Okay, you should not be confused by the fact that when I is equal to j, it should be a repeated index. It's not like that. We are talking about very specific values of the index here. So when you set I equal to 1 and j equal to 1, this is I equal to 1 and j equal to 1, and then it is just delta 1 1, and delta 1 1 is very much 0. However, if as you have seen in the previous chapter in certain problems, when we have delta ii is equal to 3. Okay, so let me just write this down as a special note, that delta ii is equal to 3, because delta ii is delta 1 1 plus delta 2 2 plus delta 3 3. But when you specifically say delta 1 1, that is simply 1. Delta 2 2 by itself is just 1, and delta 3 3 by itself is just 1. So that's how we should interpret this. There's another way of writing this in tensor or compact notation. So we write it like this fashion. Sorry. It is the trace of the epsilon. Trace means sum of the diagonal elements, and this is just the identity tensor. Okay, so these two things are perfectly equivalent. Now you see what is happening. It seems that and furthermore, please note that these relations that we have written, either this one or this one, it does contain within it the 6 independent components. So we can have an expression for sigma 1 1, an expression for sigma 2 2, sigma 3 3, similarly for sigma 1 2, sigma 2 3 and sigma 3 1. Overall we have 6 relations. Okay, so you understand that this encapsulates within it 6 relations, either this or this. Okay, same thing. And it seems that our problem is solved, because in the previous page, if we just look, we had this discrepancy of 6 equations here. We had 4 equations here and 10 unknowns, and it seems that our problem is solved. But there is a little bit of a subtlety involved. You note that although you are familiar with epsilon, but here in these equations the epsilon was not coming. Now if you are introducing epsilon in these relations, you are effectively introducing 6 independent components again. Okay, so 6 equations we have introduced, but in that process we have also introduced the 6 more unknowns. 6 more unknowns in the form of the 6 independent components of the strain tensor. Now again, it may seem like bad, but our job is almost done, because you remember from your kinematics chapter that but not to worry, because we have in our hand 6, please note this number 6, strain displacement relations. And through these strain displacement relations, because we have 6 strain displacement relations, so through these 6 strain displacement relations, we are basically connecting the epsilon ij to the displacement gradients. Okay, so it comes a full circle. We started with the unknown rho, and this unknown displacement components, and now through these various equations we have come back to this thing. So overall now this system is very much closed. So you can almost think of it like this, that this is 6 more equations. So 6 more equations here, but we have not introduced any more new unknowns. Okay, so it's like this. Let me repeat for clarity's sake. So we had one unknown here, 3 unknowns here, and only one equation here. Again, through this equation we had 6 unknowns but only 3 equations. So overall we have in our balance sheet 4 equations and 10 unknowns. So there was a 6 equation discrepancy. We managed to introduce 6 equations here through these stress strain relations, but in that process we introduced apparently the 6 unknowns in the form of the strain components. But now we have this 6 relations connecting the 6 new unknowns, the sort of new unknowns in terms of the original displacement components. So it comes a full circle and everything is nice and closed. So so the new thing that we have really introduced is basically these relations. Okay, so these are the constitutive relations. So you can write this here. So these stress strain relations the 6 stress strain relations are the constitutive relations. But again, I want to emphasize that these are not the only kind of stress strain relations. For another kind of material, maybe for rubber or for biological tissue, you could have a completely different kind of stress strain relation, perhaps also involving the strain rates. Okay, so many other possibilities are present, but for at least for a course of mechanics of solids, we'll be dealing with only this. You also note further that there is a nice connection with the generalized Hooke's law. So in first year mechanics, you had come across things like epsilon xx is equal to 1 by e sigma xx minus nu sigma yy plus sigma zz. Then epsilon yy is equal to 1 by e sigma yy minus nu sigma xx plus sigma zz. Epsilon zz is equal to 1 by e sigma zz minus nu sigma xx plus sigma yy. Epsilon xy is equal to 1 by twice g sigma xy. Epsilon yz is equal to 1 by twice g sigma yz, and epsilon zx is equal to 1 by twice g sigma zx. Now if you just map the x to 1, the y to 2, and z to 3, these 6 things is basically what you are having here. Okay, and in fact, as I had already mentioned, that if you set I equal to 1, j equal to 2, you are actually getting sigma 1 2 is equal to twice g epsilon 1 2, and you can quickly check in this third page that epsilon 1 2 is indeed equal to 1 by twice g sigma 1 2. Similarly for epsilon 2 3 and epsilon 3 1. However, these 3 relations involving the normal strain components in terms of the normal stress components, they look a little bit different from what we have here. So as one of the initial problems of the problem sheet, you will establish the connection, the algebraic connection between these material constants, the lambda and the g, with these material constants, the Young's modulus and the Poisson's ratio. Okay, so nice relations are possible between this Young's modulus, Poisson's ratio, and the Lamy parameters lambda and g, and you'll see that yourself in the problem sheet. So with this we can end the mini chapter here. There are lots of interesting things that can be developed, which is why this chapter is a mini one, but the problem sheet is almost the same length as the previous 2 chapters. Okay, so I think you'll have lots of fun with this particular problem sheet, because it'll capture many things which we discussed in the kinematics chapter, then the stress chapter, and very nicely it will be able to connect these two chapters. Okay, and this mini chapter, the knowledge from this mini chapter will be the basis of whatever you will be learning and applying in the subsequent chapters. All right, thank you very much.